Hello, my name is Laura Edmondson, and I will give a short overview of our work, Nonlinear Scaling of Resource Allocation in Sensory Bottlenecks. In biological sensory systems, information transmission is often constrained by a neural bottleneck where the number of output neurons is vastly smaller than the number of input neurons. This implies that some information will be lost in the bottleneck. Furthermore, receptors are often not distributed uniformly across the sensory sheet, but vary in their density. For example, in vision, the density of cones in the retina is much greater at the fovea than the periphery. In touch, the mechanoreceptors are more densely packed in the fingertips than they are in the palm. So, given these constraints, how should the output neurons represent the input spaces? In this example, we have a higher density region with 3 times as many input receptors packed into the same space as the corresponding low density region. If there was no bottleneck, then we might expect a one-to-one mapping of each receptor to an output neuron, leading to a proportional representation of the input region receptors. What happens when we have fewer outputs than inputs, that is, in the case of a bottleneck, and how does the representation change depending on the width of the bottleneck? We investigated these questions using an efficient coding model that maximizes overall information transmission. Information maximization is achieved by removing correlations from the input signal. Nearby receptors on the sensory sheet tend to be correlated, with the correlations dropping off as a function of the receptor distance. Crucially, neighboring receptors in a high-density input space will be more correlated than those in a low-density input space. In this paper, we show that this problem can be solved by calculating and sorting the eigenvalues of the input covariances for the two regions, shown here in blue and orange respectively. Furthermore, for certain forms of the covariance function, this can be done analytically. So what did we find? When the bottleneck is narrow, the vast majority of the neurons are allocated to the high-density input region, shown in blue, leading to an expansion in the bottleneck. For intermediate-sized bottlenecks, the allocation converges to a constant value, leading to the plateau you see here. Now, the lower density region, shown in orange, tends to be overrepresented. Finally, for wide bottlenecks, the allocation converges to a representation proportional to the input ratio. When the density ratio is larger, the representation of the low density region can be seen at smaller bottleneck widths. The width at which the low-density region overrepresentation plateaus is also smaller. What happens when we change how fast the covariance function decays? For the low-density region, a narrower covariance leads to the high-density region being overrepresented for increasingly large bottlenecks. In conclusion, limiting the number of output neurons does not lead to proportional representation of sensory receptors in the two input regions. The input region representation can contract and expand depending on the width of the bottleneck. And finally, the extent of the spatial correlations and different ratios of receptor densities also influence the allocation in the bottleneck. Thank you for listening, and please check out our paper for more details.